Yeah.
But we are also have the quasi-particles are disappearing themselves. There is less and less coherence. And
Yeah.
at some point, we cannot talk about electronic quasi-particles.
Once the Z is once the quasi-particle is completely gone. Z
So what do you mean with a Fermi surface when we don't have any coherence?
Right. So if you go back to these pictures of the momentum distribution. And okay. So the Fermi liquid, it's doing that. Right, and this is the. So in the insulator, so this is Fermi liquid. In an insulator, the water insulator, it's doing this. Right, it's smooth. So if the transition is continuous, what you could imagine happening, and you can show this in the theory that, you can calculate this as well, show that what in Berry sketch actually happens. So at the critical point, there's a kink. So this still defines a KF, even though this jump is just going to zero. It's reasonable, right? If you have a jump on one side and nothing on the other side, at the critical point, you don't have a jump, but there's some singularity yet.
But we're not talking about the same object. This in the Fermi liquid, it's well-defined quasi-particles, which are the Eigen states of momentum.
Right.
And here is something else.
So NFK, the Fermi surface is still a privileged surface in momentum space. That's where the singularity in NFK happens. It's very similar conceptually, to some extent, to the 1D London, where you don't have sharp quasi-particles, but you have some such.
I guess partly the question was this, as far as I understand. In a Fermi liquid, they have well-defined quasi-particles which are interacting electrons. In what state you introduce new particles? And so the question was a connection between original ones and the new ones that you introduce.
Oh, there's no local connection between the original ones and the new ones. The new ones are non-locally related to their non-local objects in terms of the original electron degrees of freedom. That's what one has to live with. And these weird methods, slave particle and any other thing that you can do to describe spin liquids, are somehow trying to get access to these non-local objects, which are the reasonable, they are not quite quasi-particles in some cases, but the reasonable quasi-particles on which to build a description of this thing. But they have nothing to do, there's zero overlap there, of course.
Okay. Let's start with students and then move on to former students. Yeah, go ahead.
I have a question for Steve about the spin glass. Should I feel weird that you actually have a disordered phase at low temperature while you have a perfectly ordered state spin-wise at higher temperature?
So you're talking about at very low doping coinciding
inside that AF dome, yes.
Yeah. So just to, it's where I drew.
Yes, yes.
Here's the main ferromagnet, there's the spin glass. So here it's clear what the spin glass means. You have no broken symmetry here, and you break time reversal symmetry here. Okay. Here, you've already broken time reversal symmetry and translation symmetry. So the symmetries you've broken here, it's not that the antiferromagnetism goes away here. This is coexisting antiferromagnetism and spin glass. Now, this line is well defined operationally. There are some fluctuating spins here, random, but fluctuating, which freeze at this point. The nature, or even whether this is actually a phase transition, is one of the vexed issues in the theory of spin glasses. So,
so you mean those fluctuating or freezed spins are on top of those?
right. So it's you have an antiferromagnet you also have coexisting spin glass order. The spin glass order, though, no longer breaks any real symmetry. So the mathematical description of it is in terms of replicas, and this line then is analogous to what's called a Delameter-Thales line. It's a spin glass transition in the presence of time reversal symmetry breaking, which is characterized by replica symmetry breaking. That's all very formal. It makes me nervous. I can give you maybe a physical description that makes it easier. I give the sort of construction that I learned from Centil, which is that you start by defining a simple problem that you know does just what you want, and then you try to argue that realistic perturbations don't wreck what you've just said. So imagine you have the following thing. You have an antiferromagnet, which is perfect, and then you have a bunch of other spins, and you couple them to each other with random antiferromagnetic couplings, and then they'll do their spin glass thing at some temperature, and the antiferromagnet will do its antiferromagnetic thing at some temperature. And okay, now I have two transitions, and nobody can argue with me. And now we turn on some couplings between the two. And since the antiferromagnetism has very little in the way of low energy fluctuations, it only has spin waves, and they're only in one very limited piece of K-space, then probably when I couple them together, not much happens.
Aren't two order parameters break the same symmetry coupled linearly?
Well, they're not breaking the same symmetry. The antiferromagnet preserves time reversal plus translation by one lattice constant. The spin glass doesn't have any translation symmetry. So I think it's probably correct that this line exists, but if you wanted if you wanted me to tell a mathematical physicist what it means, I would break into a cold sweat.
Well, how about a very simple way of thinking about this? So you have a small density of holes in the antiferromagnet. High temperature they're mobile, but then at low temperature they freeze in, right, into some trap, and they, they frustrate the magnetic order, and
yeah, but that's not a phase transition.
It's
That's
not
a
a phase
crossover.
Yeah,
But
it's a
there is. Well, the question was, what does this line mean that I've drawn? Is there a true spin glass transition? Yeah. So at a practical level,
so I think
there's no problem.
If people draw a line like this, it would be some kind of crossover line.
No, they've looked at nonlinear susceptibilities. They see all of the characteristic features of spin glass transition at this point. So it operationally looks like a phase transition.
Maybe if I can interfere here for a second. So we have two stories about the same topic range. And just to clarify for me, and I hope also to the audience, you presented the story about incommensurate magnetic order. And the line of incommensurate magnetic order is on top of spin glass transition.
Yeah. So the incommensurability sets in with the spin glass transition.
Yeah.
And it sets in in a continuous.
Maybe we can put both on the same phase diagram.
Yeah. So here, you would have a line here, which I call kinematic, right? And that's not a true phase transition. Right? It's a crossover, but it seems to be a reasonably sharp crossover. And one way to think about it is that it's a phase transition that is sort of smeared by this aligning field, namely the orthorhombic distortion of the crystal structure. So it's something like this. So here the incommensurability gets established, right, in the fluctuations, and then at low temperatures the spins freeze in, and they then have this quasi-elastic peak has the same incommensurability as the spin fluctuations at high temperature. So that's
there isn't any incompatibility between these. Describing this as a spin glass, I'm describing the long distance physics.
Mm-hmm.
The incommensurability is mesoscale physics. And
there's no competition.
Okay, now just there was a question. You have a question, and then
Yeah, I have two questions for Centil. First is there an example of a short-range entangled metal?
A short-range entangled metal, no, not that I know of. Since there's no example, I can't give you.
And the second question?
The second question is, so when you talk about Fermi liquid, it's a spatially long-range entangled thing.
Yeah.
But you said it's due to the existence of the Fermi surface in K-space.
Yeah.
Those gapless modes. So how can you relate this spatial entanglement to the K-space structure?
I mean, I can give you one level of answer, which so the concrete statement that I make, right, is that you take a Fermi liquid, it's a big region, and you take a big subregion, A and B, and let's say the linear size of this is L, right? And you take the reduced density matrix of A, and you calculate the von Neumann entropy. Okay. So SA. So that's the entanglement entropy. So this goes in 2 dimensions. It goes like L log L. Okay. That's different from what you would get if all the degrees of freedom were only, the shortened entanglement. That means that things here not entangled with things inside this region. So only things at the boundary. Right? So that's what gives this, that's the reason to expect this famous area law in a gap system. Right? But here it's not the area law, it's, the area would just be L. Right? Now, so why do you get this? Okay? So the physical way of thinking about it, you can calculate it in a free-forming gas, but physical way of thinking about it is that, okay, so this is in real space, right? Is to relate it to a result about, gapless one-dimensional theories. So for a Fermi liquid, after all, now let me go to K space, right? Kx, Ky. So in K space is a Fermi surface, and in the free-forming gas, I have a collection of fermions that are moving radially upward everywhere. So it looks like a collection of 1D theories. Right? Now in one dimension, you take a one-dimensional free-fermion gas, right? And you calculate the entanglement entropy. It's log N. That's a famous result. I don't know if you've heard about that, but for any 1 plus 1-dimensional conformal field theory, this entanglement entropy is log L with the coefficients just determined by this number C. Okay. So let's accept that result as given. Right? So then, since this is a collection of 1D theories, you expect to get lots of log L's. Right? So it's reasonable that you get order L log L contributions. So that's the way to understand why you get this L log L. Okay. So it's immense. It comes from this immense number of gapless modes in a Fermi liquid.
If I have a quadratic band touching or a Dirac point.
Oh, for a Dirac point, we do know the answer. For a Dirac point, because that's a conformal field theory, and for all conformal field theory, the structure of the entanglement entropy is very well understood. So you get the area law, SA, for D equals 2 plus 1 CFT. There's area law plus some gamma, where gamma is universal and is positive. And people can, and depending on how you define this region, there's all kinds of very profound things about this business. So if you do this by taking your full system on a sphere, take your Dirac theory and put it on a sphere, right? And then do this entanglement cut by looking at one half hemisphere, comparing it to the other half hemisphere. Then this universal constant that you get by that procedure turns out to always decrease under rho G flow. That's a huge result about field theories that people proved. or people found a lot of evidence for. It's a generalization of the famous C theorem to 2 + 1 dimensions. And yeah, it gives a lot of insight, and people have used that to constrain, to make all kinds of non-perturbative statements about various effective field theories that have shown up in many condensed matter systems.
Okay, thank you.
Yeah.
It's not presidential debate, but let's try to give approximately equal time to some questions.
Yeah,
Go ahead.
yeah, for Professor Kamer.
Yeah.
Yeah, we have seen with resonant neutron scattering we can probe the dispersion of phonons. I didn't really understand how we can probe electron-phonon interaction, and in particular I didn't understand the slide in which you showed that below TC there is a gap in the phonon dispersion.
Okay, so I mean the electron-phonon interaction broadens the both the phonon dispersion and the electron dispersion. Okay? And it gives a finite lifetime to the phonon, and in the frequency it gives a finite line width to the phonon excitation. And you can measure this line width. In some systems, near structural phase transition, it's very broad, so you can measure it by standard neutron spectroscopy. But in ordinary metals, this line width is of the order of microelectronvolts. And so you need this, you need the spin echo technique to actually resolve this small line width. But if you resolve it, that gives you directly a measure of the electron-phonon interaction. Right? So broader line width, the larger the electron-phonon interaction. There's actually a formula called the Allen formula that directly translates the line width into the electron-phonon coupling parameter. Okay? So now, of course, this line width can also in principle be caused by anomalicity. Right? And the cleanest way to actually measure the electron-phonon contribution to this line width is in a superconductor, because then this electron-phonon part of the line width becomes zero below the superconducting energy gap. So this is how we measure it. So we pull the system down below the superconducting transition, and then, well, below the energy gap, phonon cannot interact with electrons because there's the gap on the Fermi surface. Okay, so it becomes a true delta function. If there's a residual line width, it's due to disorder or some kind of anomalicity. Okay? But the jump in the line width gives you, at the TC, is a measure of the electron-phonon interaction. That's the idea.
Okay, but there is no gap in the phonon spectrum, right?
No. Phonon, you measure the phonon line width.
Okay.
So the phonon stays there, right? It stays there even without electrons.
Okay.
Okay. It's just, without valence electrons, of course. So it stays there, but it now becomes a delta function execution.
Okay, perfect.
Okay? So the line width as a function of energy, that is a measure of the gap.
Thank you.
Okay, questions for Steve? Please.
So in the lecture you talked about if the SO3 symmetry is broken to the crystal field, then the eigenvalue problem will be even though the representation are the same, but if they are originated from different orbitals, then they will evolve independently under RG. Am I correct?
Okay.
Maybe you can quickly, what is the question?
Yeah, so I think the question is if the band structure doesn't have full rotation symmetry due to crystal fields. Or put another way, if we classify the pairing states simply by the point group representations, that's a small number. But they're an infinite number of eigenmodes of the pairing operator. So there's no symmetry that stops them from being mixed with each other.
Yes.
Nonetheless, under RG, they develop completely independently of each other.
So you mean the same point group representation originated from different orbital representation?
No, I mean, it could be a single orbital band structure, or it could be multi-orbital band structure with many Fermi surfaces. It's a very general statement. So, I mean, what the modes are depends on what the interaction is. So we've got some interaction, V of K, K prime, where K and K prime are defined on the Fermi surface. So, I don't know, maybe the Fermi surface looks like this, it's a square, maybe it's got a couple of other things like this. All right, I don't know, something like that. And so there's only a few symmetry classifications, but since K can take any point on this Fermi surface, this is an infinite by infinite dimensional matrix. So this has an infinite number of eigenvectors and eigenvalues. Obviously, ones that transform under different point group symmetries can't mix with each other by symmetry. So, all right, so there's only infinity divided by 6 eigenmodes in each symmetry class. But still, there are those many modes. I find them for my initial interaction, and I find that each of those modes grows independently of the others.
Maybe this is just related to the previous question. So in Professor Sigrid's lecture, we saw that if you have a repulsive interaction, and in the K-space, if you expand it in terms of spherical harmonics, one of the channels will end up giving you an attractive interaction.
Right.
So similarly, so I'm trying to see a link in the RG picture. So if you have an RG transformation matrix, will such similar symmetry arguments will lead to BCS kind of attractive?
So as far as I know, on the lattice, it's not possible to prove a general theorem.
Yeah, there's no general theorem.
However, we've looked at a shitload of examples with repulsive interactions and finite range. So, I mean, if you have the Coulomb interaction, I don't know. I also prepared to walk. But if you have an interaction that's repulsive and say 0 beyond this distance, we've looked at lots of such examples. You always find that there are some negative eigenvalues which then grow under RG. And they're always such that their average around the Fermi surface is 0. That's to overcome the first order repulsion. But then they could have different shapes, even different symmetries, depending upon details of the band structure. So for cuprate-like band structure, we'll see. I mean, this is something I'll cover. They'll very naturally have D-wave symmetry. For nictide-like band structures, they'll have S-wave symmetry. You can get any symmetry one. If you actually, interestingly, if you take a band structure that looks like the pseudo-gap phase and then try to do this, you'll find not D-wave, you'll find G-wave.
G-wave?
I think so, not G-wave. Yeah, G-wave, right?
Is there such a thing as G-wave under the currents?
Cosine kx minus cosine ky times cosine kx plus cosine ky, whatever that is.
Cos squared kx minus cos squared kx.
No, no.
Cosine
kx minus cosine ky times cosine kx cosine ky. Yeah.
Yeah, so I have to make a non-physics comment because I'm going to have to run off. So there's 2 important changes. Sorry about that, everything's still in flux. So first, dinner is actually not in C4C, it's going to be in the Weather Tap Cafe, okay, where we had the registration. It's in C4C, but in the basement there, if you remember. And it's gonna be a special dinner, the kind that we're gonna, at least in part, the kind we're gonna have on Flagstaff. So there'll be wine and things, okay? Second thing is, the bus is not leaving quite from Kittredge, it's close to Kittredge. It's actually on the south side of C4C. Before you cross the road, there's something called bus loop, which I don't really know what that is, but it's on the south side of C4C. Which means on the side of, looking towards Kittredge.
And the time is the same.
The time is the same, be promptly there at 6 o'clock, and Shao will coordinate to get you there.
And when are we going to get back here?
Huh?
When are we going to get back here?
Depends on the weather, but nominally maybe 8 o'clock, maybe 8:30. Some people may decide, if the weather's good, people may decide to hike down. Dinner's 5, and you'll go till a little bit before 6. Walk out.
8 to G.
Okay, sorry, but that's important, you can make a note of that.
Okay, one more round of questions. Let's see. Let's start with you both. Go ahead.
Sorry.
Yeah.
Can you comment
Go ahead.
on the magnitude of U effective in what you were deriving? So before you integrate out above a momentum shell lambda,
Yeah.
you have a base argument on the fact that U effective at the UV is small.
Yes.
So and that's completely dependent, right, on different UV scenarios. So in which case is it actually small, in which case is it not small?
No, so I was doing something, so again, I wasn't trying to solve any particular material. I was trying to solve a specific problem. The specific problem is, wrote down some model on the lattice even. I went all the way to the UV, but in which the interactions were arbitrarily weak. So it's not a question, it's the condition for my solution to be valid. It is a solution that's asymptotically exact as all the interactions go to 0. There's a deeper question about when such solutions tell you anything about real problems where interaction strengths are not small. Okay, we can negotiate about that, but here it was much simpler than that. It was just by assertion.
Okay. Question for President Kainer. Yes.
So this is probably maybe jumping ahead. You've talked about the magnetic excitation as mentioned in neutrons. I assume you're going to talk also about the charge as seen in X-rays. And this is a relatively recent development. To what extent do you think that that spin, that spin density wave correlations in the region are ruled out in the region of the Kubrick phase diagram where a charge order is seen?
Well, you can rule this out by just USR experiments. And USR is a very sensitive local magnetic field. There have been some reports in the past of tiny local fields like USR. In this regime of the phase diagram, we do have charge order, but they later turned out to be spurious. So at the moment, there's actually, at least in YBCO, there's no evidence of static local fields. And you can set a very stringent upper bound by USR, which is very, very sensitive technique. So, of course, in the lanthanum strontium copper oxide material is different. So there you always have really critical spin electronegations over a wide range of doping. But that's anomalous. So in many other, I would say most other cuprates at moderate doping, you don't have magnetic doping. At least in simple cuprates. There are multi-layer cuprates where the outer layer and the inner layers have different doping levels. So their magnetism and superconductivity also coexist over a large range of stoichiometries.
Okay, last question for Santil. I think you are already asked. Yeah.
Well, my question is, so I think the rate particle construction is trying to capture some kind of entanglement property of the state you want to describe. So is it obvious how it is considered in this formalism? I mean, my question is what kind of entanglement is captured?
Yeah, it gives you access to these non-local quasi-particles. So another way to say it is that, let's take the fractional from Hall effect. Everybody understands fractional from Hall effect. Let's take that. So, the two quasi-particles in the fractional from Hall effect, the Laughlin 1/3 state, or these Laughlin quasi-particles. So you'll never access that through any mean field theory that you do to the original electron Hamiltonian with, by doing any ordinary Hartley fork. Gives some expectation values in fermion bilinear, product of four fermions, none of those things will ever access this state. So you have to do something weird that enables you to access these non-local degrees of freedom. So the reason that won't work is because this Laughlin quasi-particle, it's an anyone, right? It's non-local. It has non-local interactions with each other. It carries fractional charge, so it can't be created by local operators. So how do you get access to those kinds of things? So the photon, the slave particle thing, sometimes people call it photon. Okay. So that kind of description, where by hand, let's say you write your electron as a product of, to generalize this construction spin liquid, you write the electron as a product of three fermion operators. Then it's a weird thing to do, but at least you produced, your starting point is that you're writing your electron in terms of three things. And the Laughlin 1/3 state, that's the physics of it. The electron is a composite of three of the quasi-particles of the Laughlin state. So then you can try to work with these photons, these objects, and try to see if you can build a state in which they survive as in some form as quasi-particles. So that's the idea, that you want access to a state which has this weird entanglement which enables the quasi-particles to have highly non-local interactions, to be non-local objects. So the slave particle thing is a way to get access to those states.
But what type of configuration is captured is not clear.
Sorry?
What type of configuration is captured by this wave that is not?
What type of configuration?
What type of entanglement pattern? Maybe I'm not sure what it is the right word to use.
Yeah. So the magnetism context or the Hall context, there are some kinds of entanglement that are legal, and some things that you can imagine, but they are illegal. So if you did the theory correctly, then if you just followed this formal route that is sketched, you make a slave particle description, write down some mean field, and then try to do fluctuations, and then ask about whether this resulting effective field theory gives you a stable phase or not. So if it doesn't give you a stable phase, then the picture that you have for the state is wrong. The pattern of entanglement that you imagine for the state is wrong. So let me give you a particular example of that, and then maybe we should stop. Okay. So in the quantum magnetism context, there's this model that Steve introduced, the quantum dimer model. So you can think about it on various lattices. Right? Now you can represent the states of the quantum dimer, of the quantum dimer model, this mapping to configurations of loops. Okay. Now on a square lattice, these loops can be oriented. Okay. And then you can imagine a liquid phase of these loops, dimer liquid, where these oriented loops have formed some sort of liquid. Now you can also do this on a triangular lattice, where it turns out you can't orient those loops. So then it's the corresponding wave function would be a sum over unoriented loops. Right? So both are things that you can imagine. Now it turns out that this oriented loop picture doesn't give you a stable state.
In 2 dimensions.
In 2 dimensions.
It does in 3.
Yeah, I know it does in 3, but as an example of how something that you imagine may not work, the 2D is a good example.
Yeah.
But in 3, but the unoriented loop is something you can imagine, and it does work. Right? And we can understand this through effective field theories, blah, blah, blah. Right? So, both are different patterns of entanglement that you can imagine, but only one thing is stable. The other thing is not allowed. So this field theory approach enables you to address questions of this sort. Right? Which thing is allowed, which thing is not allowed, but in the field theory approach, you have to imagine it, you just turn the crank.
Okay, and with this, let's thank all speakers.